Okay, welcome to lecture 21 of PDEs in the year 21. Today we're going to be changing, basically looking at a different technique to solving differential equation called separation of variables. It's complementary to finding Green's functions. It's also the technique I try and execute first, because if you can use it, you have a very good intuitive feeling for what the solution is. You have a very reasonably quick way of finding it, and it's much easier to actually do the calculation. In fact, it's my favorite technique for solving these things. It's also the technique that basically most of the major results in quantum mechanics and almost any analytic solution of differential equation was initially found in. The Green's function stuff developed alongside it, and it was very useful for electromagnetism, but it's also more complicated to execute, whereas this thing is quicker. The only problem is it's not always possible to do, and that's something we're going to explore today. There are only certain problems that you can solve in this way. If you can't, then you must go to numerics, or you must do use Green's functions or something like that. And basically what I'm going to do today is tell you, look at a whole bunch, look at what it is, separation of variables, look at a whole bunch of solutions that result in a whole bunch of equations that result in similar solutions. And then I'm going to look at what coordinate systems actually makes it possible. I'm actually going to try and quantify, just in 2 dimensions, what coordinate systems permit separation of variables. And this is something I didn't learn when I was your age. I just learned about the technique. And then the problem is, then you find an equation and you try and solve it using separation of variables, and it might not be possible, but you don't know. So, and then much later I learned that there is actually just certain coordinate systems in which it is possible, and once you've examined all of them, that's fine. So I'm going to give you the benefit of my experience just in 2 dimensions. And what I am going to say is a similar thing, or a similar way of classifying things actually exists in 3 dimensions, but we're not going to do it. You can actually look up separable coordinate systems in a book called Morsch and Feshbach. They actually have listed all of them, and people have found them, and it's good to know that it at least is there if you try and solve a problem using it in 3 dimensions. And why on earth it did that is a mystery. Okay, so the separation of variables only in 2D. And sorry, my screen is now frozen. Okay, and now what I'm going to do first is I'm going to list all the possible problems where you could use this technique, and I'm going to give you the first inklings of what it is and how it goes about it, and then I'm going to, in the next lecture, do some of the fundamental theory that allows you to do it in general. Okay, so the separation variables in 2D, just to define things that I'm going to use just now, you first have Laplace's equation. So that, if you remember correctly, if you're in 2 dimensions, you just have that differential operator. We've looked at it a lot. One, in certain systems, you can separate that, and I'll show you how in a moment. But before I do that, I want to show you that a lot of problems we've been looking at eventually become similar. You use this exactly the same technique for them if you're using separation of variables. So to see how this happens, let's have a look at the wave equation, right? And this is going to be our first example of what separation of variables is here's your wave equation. You have your Laplace operator minus the second derivative with respect to time of psi. And what you usually do with separations, or you effectively do, is you make an assumption about the nature of the solution. Here you make the assumption that you can actually write it as a product of 2 functions of the variables independently. Okay, and this is why it's not always possible to do this, but it's a good guess to start. So you usually do this, plug this into your equation, whatever it is, and see if you can actually separate the things out. In other words, you can get one side of the equation that is functions only of time and one side of the equation that's functions of the other variables. And that is where the techniques comes from. So to see how this works, you assume psi has this form, you substitute this form into your original equation, and when you do that, you see that the Laplace operator, that's just derivatives with respect to the spatial coordinates, gets applied only to phi, and the time derivative then gets applied only to f. Okay? And the next step is to see that you have functions of two different variables, and to try and put a function of the variables of a collection of variables on the one side and a collection of the other variables on the other side. And the way you can do it here, it's not the only way, is you can divide by f phi. So if you divide by f phi and you shift everything that's dependent on x1 and x2 to the left and everything that's dependent on time to the right, then you have that equation. And the separation ansatz comes where you say, look, this thing is a function of two variables that are independent. This is a function of a third variable that's completely independent from the other two. This equation, and it's got to be held true for all those variables, this equation can only be true if each thing independently is equals to a constant. So what you can say then is, if both the left-hand side and the right-hand side are independently constant, this thing is true. So it actually allows you to separate this ordinary differential equation of three variables into this partial differential equation of three variables into two different equations, one which is an ODE and one which is a partial differential equation for a lower order system. So we're going to call this constant minus k squared, and then what you're going to have is, if you put this thing equals to minus k squared, you've got f double derivative is equals to c minus c squared k squared f, and I've just called omega c squared k squared. Okay, so this thing is now an ordinary differential equation which you can solve because it's just a harmonic oscillator. So you have the time dependence which is going in there that you solve separately up to this constant, and what is left over is this thing which they call Helmholtz's equation. Okay, and we're going to look at this. So I'm basically, so far we've looked at Laplace in space. In this example, we've reduced the wave equation to an ordinary differential equation in f and a spatial Helmholtz equation over here. And it's not the only equation that we can do that. If we now look at the diffusion equation, we can go about and do exactly a similar thing. We once again have the Laplace equation times a constant minus the first derivative with respect to time. We are once again going to assume that it has a certain structure. In other words, that the time dependence factors out from the spatial dependence. And if you do that and push it back into this equation, you once again get this expression where the Laplace operator only goes to the functions that are dependent on space, and the time derivative is only applied to g, and that's equals to 0. You divide by g phi and collect things of like independent variable on the same side. So here you once again have Laplace's equation over phi is equals to g prime over g kappa, so it's only a function of time, and that once again can only be true if both sides are equals to the same constant, which I call the separation constant, and here I'm going to call it k squared. So you can see immediately you can solve this equation for g. Okay, the first one is then Helmholtz's equation exactly like what's down here. The second one you can actually solve explicitly for g, it's just an exponential. And you can recognize this exponential decay because this is the thing that appeared when we looked at the solutions for the heat function. Remember we had the Green's Green's function for the heat equation, and it also had this exponential decay. And so in the separation of variables, the exponential decay becomes obvious because you've made this ansatz. Okay, so G is then known up to this constant K that we don't know, and we must still solve the Helmholtz equation in 2 dimensions. Okay, so this is an example, both these are an example of separation of variables, but what's going to happen is we're actually going to be able to go one step further in some coordinate system and actually try and solve this Helmholtz equation separable as well. Just one more example that actually fits into the same class of equations like this is the Schroding equation, which is famous from quantum mechanics. Okay, it looks like this. It's a complex equation that's basically a heat equation for the probability distribution. So it gives you an idea of how the probability that a particle is somewhere becomes more and more vague as time goes on. That's basically what it says. So the psi you can view as a probability cloud that describes, for example, the position of a particle, and quantum mechanics has shown by comparing with experiments that it's basically well described by this, where you have the Laplace operator times by some potential that the thing is moving in, which is typically like the potential of your atom or an electric field or something else that you've created mechanically for your thing, and that's the quantum mechanical equation. Once again, you can make an ansatz that says let psi be the factor of these two. If you put that in, you have basically the time derivative only operating on f times phi is equals to f times the spatial operator applied to phi. You divide by f phi, and you add the separation constant, and you have that f prime over f is equals to some constant. And the spatial part is that this thing is equals to that constant, where E is now a separation constant. Okay, and so the time dependence, once again, you can easily solve f. This is just an exponential decay, much as the heat equation, except now that you have a complex time. And this type of function over here is still in 2 variables, and it's this class of equations that we're going to now, in other words, look at the Schroding equation is basically Laplace plus some function times phi. Helmholtz is Laplace plus kappa times phi, and the Laplace equation is just Laplace itself. Okay, so it's now those operators that we're going to look at the next slide and try and separate them further. And so let's go on, and we look at Laplace's equations. And I just want to give you a slightly more rigorous definition for separable differential equations. If you have an example in 2D, is separable in a given coordinate system. And this is important. It's possible to have a differential equation that's separable in one coordinate system and not another one. And this is what makes it hard, and this is what I've spent hours of my life doing, is changing coordinate systems and hoping my equations are going to become separable, and then it didn't. And then eventually I realized, oh, look, there is a way of actually classifying all these coordinate systems in 2D that it's separable in, and this is what I'm going to do now. So it's to save you time in the long run. Okay, so PDE in 2 dimensions is separable in a given coordinate system if it can be written as 2 ODEs. Right. In other words, if we can do the trick we did with time and separate it out. And typically, you want the PDE to be separable, and you would ideally like it separable in a coordinate system in which the boundary in which you want to find the solution is actually one of the coordinates that it's separable in. That's the best thing, because then it makes it very easy to specify your boundary conditions. You know, like we specified the initial value problem with t equals to 0. We would like to have that equation separable where we can say on a fixed coordinate, that's the one boundary. So let us consider this differential equation, the first one. Okay, so this basically includes the class of all the equations that we looked at on the previous slide, or that we derived on the previous slide, where f is a function of the two variables. So phi is a function of two variables, and f is a function of two variables. And f can be 0, which is true of Laplace's equation. It can be k squared, which is true of Helmholtz's equation. And it can be, in general, a function of x1 and x2. Okay, so we're actually going to look at all three possibilities and classify all the coordinates in which this is possible, and therefore all the problems that you should actually try and look for separable solutions. Okay, so now let's work out when it's separable. So we said the system is separable in a given coordinate system if we can basically write it as two ODEs. So we're going to make this ansatz. Again, it's an assumption that phi can be factored into two separate functions of the independent variables. We substitute it in to 1, and just as we did in the examples on the previous slides, we're going to divide by the two functions, and then what we're going to get is this expression. We're basically going to get that the second derivative of p1 with respect to x plus the second derivative of p2 with respect to x2 over p1, and this one is over p2, plus f of x1, x2 is equals to 0. And so we can have, in this particular coordinate system, that this thing is separable if and only if f is separable. Okay, so equation 1 is separable in Cartesian coordinates, basically the coordinate system we started with, if and only if you can write this forcing, basically this function that enters it as a sum of 2. Okay, because the moment you can do that, you can then group the f1 of x1 with that differential operator, and you can group f2 of x2 with this one, and put the one on the left-hand side, one on the right-hand side, and then you have two different ODEs. Okay, so if that is true, the equations decouple to this equation, which is equals to a constant beta, and that equation, which is equals to a different constant. Okay, and we call this constant beta the separation constant. Right, so what is also true is if you change variables and you've transformed Laplace's equation, I think, in like cylindrical coordinates, then you get a different differential operator. And then potentially you can also get the function can become separable where it's not separable in the original set of coordinates. So what we're going to ask now is how you go about actually seeing how you go about seeing in what coordinates a certain operator is separable. So the first thing we're going to do now is, so we've now defined what it's separable in Cartesian coordinates. We're going to now look for other separable coordinates, and we're going to go back to our old friend, the complex analysis story, because there is an intimate connection between Laplace's equation in 2D and complex coordinates. And the reason why it is so useful is because conformal transformations has many properties, but the one property is it keeps your coordinate system orthogonal. Okay, so you still, if you have a grid and you do it like Cartesian grid and you transform it into, use complex transformation or conformal transformation to transform it into another grid, the lines still remained orthogonal to each other, and the differential operator looks very, very similar. Not exactly the same, but very similar. So we're basically going to work out the consequences of a conformal transformation for this differential equation. So it's z be the complex number of the two coordinates with its complex conjugate. Then we can write the derivative with respect to x1 simply as dz plus dz bar, and the derivative with respect to x2 simply as I dz plus dz bar. Okay, so it's just an ordinary transformation, except we've elevated our variables to complex variables. And then what we can do is we can write the Laplace equation plus, or basically our generalized Helmholtz equation plus this function times phi, in the new coordinate system, we can show that it's equivalent, if you simply write the things out, to 4 times d phi dz dz bar plus 4f phi. I think you've done this. I think I did it right in the beginning when we did Laplace's equation first. If you don't know where this comes from, take a very careful look and find out. Okay, so now let's use this to transform to the new coordinates. And writing it this way actually makes it very, very easy, because we're going to say our new coordinate system is z equals to an analytic function of w, where w is just the new set of variables. Okay, so this is how we're ensuring that we're doing a conformal transformation. In this assumption is basically the fact that the transformation is going to preserve the fact that our coordinate system is orthogonal, and I'll show you a few examples. So now we have 2 new coordinates, xc1 and xc2. We have our old coordinates as functions of xc1 and xc2, and that function is determined by this function that drives the transformation. Okay, so if we now want to transform the coordinates, the easiest thing to do is just to look at this thing. You have d phi dz bar, which is basically the same as d phi dw bar dz bar, and then taking the derivative with respect to z is just ddw times dw dz. Okay, so using the conformal transformation makes it very easy to write down what the transformation does. And so an equivalent way of writing it is, if we remember just from this expression up here, that the Laplace of phi in the original coordinates is just 4 times dz dz bar, we can simply write this thing as 1 over 4 times dxc1 xc2 plus dxc2 dxc3. So it's once again Laplace's equation except in the new coordinates. But this dw dz, dw bar dz has given you, is the same as saying it's 1 over g prime, the derivative of your transformations, norm squared. Okay, so those 2 terms is simply equals to the square, 1 over the square of the norm. Okay, so we see that we've got Laplace's equation in the new coordinates times this factor that multiplies it out. And so if g prime is not equals to 0, the derivative is not equals to 0, which will basically always be true if you have a valid transformation, okay, then all the coordinates obtained by a conformal transformation from the coordinates, from the Cartesian coordinates, are separable for Laplace's equation. Okay, so because Laplace's equation is basically with f equals to 0, you can then multiply through by this g prime, and you're left with that thing equals to 0, which we know is separable. Okay, so if you're solving Laplace's equation, the trick is to find a conformal transformation that has one of the conformal variables corresponding to the boundary of your domain, and then you have a separable solution. You can always apply separation of variables. Okay, so f equals to 0 is very nice. K, with the moment you put a f here with k, you can see you have a problem, okay, because you can't multiply through by the norm of g prime squared, because you're going to have k times g prime squared. So that thing is only going to be separable if that g prime squared is separable. Okay, so this is Laplace is always separable. If f is not 0, then the expression that you get is that thing, right? Where I've just multiplied through by g prime, the norm of g prime squared, times f times phi. And so that thing is separable if in the new coordinates this thing is separable. Okay, so we have a new criterion, and now you can see why even if it's not separable in one coordinate system, the possibility exists that it may be separable in the other. Okay, and so this is all I learned, and then I was trying all sorts of transformations and never getting to a separable thing until I realized there was actually a way of systematically looking for it. Okay, so this is now the criterion. If you do a conformal transformation, the derivative of the transformation times f, if that's separable, then the thing can be separable. And to actually look for it, it's very difficult to see if you can write a function like this, but it's much easier to take derivatives. So this expression here, or this condition, is entirely equivalent of saying if this thing's derivative with C1 and C2 is 0, then it's separable. So I'm just rewriting the condition for separability. Okay, another way of writing that is also equivalently to saying this. So if you have the norm in terms of W rather than the new coordinates, you can carry out this check as well. But just remember that you have to transform f, which is a function of x1 and x2, into C1 and C2 before you work out the derivatives, or W and W prime before you work out the derivatives. But all these three conditions now become the criterion that your equation is separable in your new coordinates. Right, so now we're going to actually examine them for Helmholtz's equation where f is a constant. In other words, we're only going to examine whether this criterion is valid or whether that criterion is valid, because f can just factor out. Okay, so Helmholtz equation, f is a constant, just rewriting what I had in the previous slide. It's separable if and only if, I'm just going to use this criterion, that thing is true. And writing this thing out, I can actually do a separation argument. So I apply this operator. This first one applies only to the first derivative, to dz dw. The second one applies only to dz bar dw bar. And if I can then separate it out, I have these two equations. Okay, they are themselves separable. And that's only true if it's equal to a constant. Okay. So what I then must do is I must solve this complex equation as well as its complex conjugate to try and find all the possible coordinate transformations that will actually give me a separable Helmholtz equation. And let's do that. So the first options that I'm going to look at, if lambda is equals to 0, it's a fundamentally different equation than from when lambda is non-zero, okay, because you've lost this derivative operator. So if lambda is equals to 0, you're basically solving that equation, and that one's easy to solve because the third derivative vanishes. It can just be a polynomial of the low-order derivatives. So there, if lambda is equals to 0, z has this possible expression. It's quadratic in W. These things are complex constants, and remember this thing is a complex number. So this is where it becomes a little, not tricky, but it's just the complex, the whole transformation is dependent on this expression, and it's different from the real component. So just let's write it out. So suppose, let's look at the first case, right? Let's just put alpha 2 equals to 0 for a while, and let's see what this transformation does. So suppose z is equals to alpha 0 and alpha 1 times w, where these are complex numbers. And let's now write out the implications for what it actually means for the coordinate transformation. Okay, so if you have this transformation and you write out the real and imaginary part for z, you write out the real and imaginary part for w, you multiply it by alpha 1, which is equals to that. What you get is this expression. Okay, so the real part gives you, for alpha 0, it's just a0, which goes into x1. For x2, you have the imaginary part, which is b0. So that's the first contribution. And then over here, you have the real part of alpha 1 times the real part of w1 minus the imaginary part of alpha 1 times the imaginary part of W, which is xc2. And then here you have the imaginary part of alpha 1 times the real part of W plus the real part of alpha 1 times the imaginary part of W. Can you tell me what this transformation does? You should have done it in your first year. So look at the first term. This transformation can move the origin, right? So it's basically x minus a0 and x2 minus b0. So it's a translation. That's what the first term does, right? So it moves the origin. The second term, look at the structure. It's basically a1 minus b1, b1 plus a. So suppose I were to put a1 equals to r cos theta, b1 equals to r sine theta. What I would get is basically something. Now I'm going to have to, I wonder if I'm going to reach with a mic. I'm basically going to, if I have a1 equals to r cos theta, b1 equals to r sine theta. Right. That second part, what I'm basically going to get is something that looks like this times r times c1, c2 times cos theta minus sine theta times sine theta cos theta. Okay, so that's just another way of writing that transformation. And that thing is a rotation. The matrix rotates what C1 and C2 is, and R scales it bigger or smaller. Okay, so basically what that transformation represents is a translation in the constant term, a rotation, and a change of scale. Okay, so if you started with Laplace's equation, or in fact Helmholtz's equation, and you had it on a funny shaped box that was rotated out somewhere randomly in your coordinate system, you would execute a thing like this that would put your coordinate system in the middle of the box, and then you could orientate your new coordinates to actually go with the boundaries of the box. Okay, so simple transformation, simple argument, but you had to have those things at least to have a valid coordinate transformation. So it's kind of nice. You derive your result, but then always look at try and find a way of what it means. Okay, so we know what the basic two things is. Okay, so those are the first two terms of what that transformation does. The second one is slightly more interesting. So let's just study it separately. Let's put z. Let's look at the example where we have z equals to 1 over 2 w squared. Okay, if we do the same thing, we now have that x1, which is equals to the real part in the new coordinates, is basically x1 squared minus, xc1 squared minus xc2 squared, and x2 is equals to xc1 xc2. So it's basically what they call parabolic coordinates. So the way to think about it is you can transform your differential equation into these new c coordinates, right? And then you're finding the answer on a square grid like that, because where it's separable. And look, I've put different colors over here to actually show you where the coordinates are. And then you can write your solution down. The equation is separable in these new coordinates. And then you can actually transform the answer back to your original coordinates. And then you can see what these lines actually look like in the original coordinates just by simply using these expressions. And so in the original Cartesian coordinates, these lines correspond to parabolas. Okay. So in the original Cartesian coordinates, for example, if you have, can't see nicely now from this angle. I think this is, so suppose you hold, for example, C1 constant. Okay, so let's say C1 is constant over here. Okay, then you have x2 is equals to C2 times some constant. And then you have x1 is equals to C2 squared, minus C2 squared, or basically some constant minus C2 squared, which is basically some constant minus x2 squared. So you basically have a parabola that's on its side like that. Okay, and you can do that for every single line over here, and then you can actually see the lines that I've drawn correspond to the actual parabolas in there. So typically, if you wanted to solve heat flow on an aircraft wing, right? The aircraft wings have this type of shape that's made out of aluminium. You would think, oh, it's a very complicated problem. What happens if I put a flame over here, or what happens if that jet engine heats up the equation, the aircraft wing over there? But actually, you can take this shape, transform it using a very simple coordinate transformation to solve it on basically Cartesian coordinates, and then take your solution, interpret it back there. Very, very powerful technique, and you can get a lot of insight into how the solution actually behaves. Just another thing to look at what this transformation does at every point over here. If I drew it to scale, you'll see that the lines cross at right angles. Okay, that's one of the features of your conformal transformation. Okay, so nice trick. Right, so we've now done with the case lambda equals to 0. The only possibilities that will give you a separable solution are your translation, rotation, and change of scale, which is linear, and then this quadratic thing that will basically take a wing like that and transform it into flat space. Sorry, into a grid. Now the next one, and this is just for Helmholtz's equation. Okay, so the next case we're going to look at is this thing. Okay, where lambda is not equals to 0. Okay, and we're going to look at where lambda is equals to 1, and that's all we have to consider, because suppose lambda is equals to a, which is not equals to 0 and it's not equals to 1, you can simply rescale all the coordinates together by a factor so that lambda is equals to 1. Okay, so you only have to worry about lambda equals to 1 when you explore all the possibilities. And so what we want to solve is this equation in general. Okay, and to solve this equation, you can simply consider dz dw to be the variable, and then you have two derivatives with respect to w of dz dw is equals to the variable itself, and so it's a harmonic function. And so you can actually write down the general answer for this equation, and it's just the exponential functions and then an additional constant. Okay, so this once again is the general solution for this equation, and so we've basically got all the general solutions for the separability condition now. In the case where lambda is equals to 0 and lambda equals to 1, that's all the possibilities you have for separable coordinates. Done. Don't look for any others, you can't find them. Okay, so here, once again, this beta 0 term is just a constant term, so it corresponds to shifting your origin. But these guys are a little bit more complicated, and so we'll look at what they mean now. Okay, so we're just going to massage it a bit and actually write out the real and imaginary parts. So here we go, z is equals to e to the w. This is just one example. And we're going to set E. So I've put beta 2 equals to 0 and beta 1 is equals to 1. Okay. And so you have E is equals to that. Let's work out the real and imaginary part of this exponent. So it's basically where E1 and E2 are real. So you basically have x1 is equals to e to the c1 cos c2. And x2 is equals to e to the c1 sine of c2. So this actually is polar coordinates. Okay, so polar coordinates is a separable coordinate system, which we expect because we've been using polar coordinates for finding some of the solutions on the disk and stuff. Okay, so we now know why we used it. It's because I knew you could write down the answer there. Okay, so polar coordinates, and you see this, if you put r equals to ln of xc1 and phi equals to xc2, then you have your polar coordinates. The second case is, and I'm not even going to draw the picture for that, I'm going to do the more complicated one. If you have z equals to beta 1 e to the omega and beta 2 equals e to the minus omega, and you now want to express that, and I'm going to assume beta 1 and beta 2 are actually real rather than complex. I'm going to set e to the a equals to this expression and e to the b equals to the ratio of the two. And then this transformation is equals to that thing, which I can then write down as e to the a cosh of w minus b. Okay, and if I go one step further, I'm further going to assume that d e to the a is a real value and b is a real value, and then what this coordinate transformation basically is, if I write out this cosh in terms of its real and imaginary part, it's simply cosh, the real part is just c1 minus b times cos c2, okay, and the second one is d times sinh of c minus b times sine of c2. Okay, so this now becomes the real coordinates of that complex transformation. Okay, so that's why I said the complex transformation is very powerful for transforming the coordinates, but there is a bit of massaging to be done, not uncomplicated massaging, but when you actually want to understand the coordinates, you must make explicit the real and imaginary parts. Okay, so let's see what this thing actually does. This is a system of coordinates that they call trigonometric elliptic coordinates in R2. And so I'm once again going to look at the coordinates x1 and x2. So x2 goes from 0 to 2 pi. Okay, so it's on this axis over here. So there's 0, there's 2 pi. And x1 can go from, say, 0 to infinity. It can be anything. Okay, so I'm just going to look at what this thing translates to if I choose b equals to 0. Okay, so b will just shift the origin of x2. So it doesn't matter if you choose it to 0, but the corresponding Cartesian coordinates is basically ellipses, right, in the circles, and hyperbola in the other direction. So, for example, if you pick a certain line here, say where c2 is equals to, say, for example, that line over there, right? c2 remains constant, so you've effectively chosen a constant angle, and then you have c1 varying. So you basically have something that comes in like that, gets to that point, you have a hyperbola, and then goes out again, because cosh of x1, sinh of x1 will actually give you a hyperbola. So you now see that this thing, it's almost basically a polar coordinate, but inside here it's spread out, and that's what the elliptic coordinates are. Okay, so the polar coordinates are actually a special case. And that's it. Those are all the coordinates that are separable in 2 dimensions, right? Translation, rotation, and scaling. That's the linear transformation. Then you have your parabolic coordinates that we did in the previous slide, your polar coordinates, and then the general case with the elliptic coordinates. And that's it. Okay. So now we know that's true for Helmholtz equation. We know Laplace is always remains separable. Let's see what happens to this thing in Schrodinger's equation. When is Schrodinger's equation separable when you do a coordinate transformation? And it turns out not every Schrodinger equation can be separable. But you can write down a list of all the equations that are. And so how you do that is what I'm going to do in the next slide. Is the separable Schrodinger potentials, like the particular coordinates, the particular Schrodinger equations that are separable, you can write them all down knowing what you already know. And the way you do that is you look at, transform the Schrodinger equation or the sort of the spatial part into the new coordinates. Okay, so remember we had this expression where you have the Laplace in the new coordinates equals to this transformation squared times f of g. Okay, and you knew that it's separable if and only if this criterion is met. Okay, so that's the condition we're trying to satisfy. And now what we have is if f, which we don't know, has this form, okay, for every x1 and x2, we know that at least it's necessary for this e term. In other words, if you want the thing to be separable in general, this term must be separable and this other term must be separable. So we know it's necessary at least to have a coordinate system in which Helmholtz's equations are separable. Okay, so we're going to then transform that to that equation. So transform to C1 and C2 and check that that thing is 0. It's necessary for the thing to be a subset of all the separable coordinates for which Helmholtz is separable. So you only have to go about checking all those things we had on the previous slide. Okay, so that's important. If we are in a coordinate system for which Helmholtz is separable, we can use those results to actually write down the general case in which the things are separable. Okay, so we can construct all the possible separable potentials, and the way we do it is we choose a valid coordinate system, either parabolic, polar, or elliptical, for Helmholtz's equation. And then any separable potential in that system of coordinates has the form that. Okay, so it actually allows you to write down what V C1 and C2 is. It's simply separable functions divided by this coordinate transformation, but that coordinate transformation is actually itself separable. You can always write it this way because of the fact that Helmholtz's equation is separable. So that then gives you the most general expression for what the potential is. It's basically the rational function of an arbitrary function f1 of c1 plus an arbitrary function f2 of c1 divided by these two functions that comes from the separable coordinate system, and you're done. There's no other system for which you will be able to find a separable coordinate system. Okay, so that basically concludes the lecture for today on separable coordinate systems and how you find them. What I'm going to do next time is I'm actually going to look at what we know about ordinary differential equations that actually makes it possible to solve that equation in general. So today the one example that we came with was the harmonic. Basically, the harmonic two derivatives of the function is proportional to the function. That's the simplest example. there are more complicated equations that you can get, and the easiest one that you can see is if you actually write Laplace's equation in polar coordinates, right? Then you have two derivatives of the function plus 1 over r times the derivative of the function. So we're going to look at general techniques of solving that thing as well. And it turns out that there's some very powerful theory in ODEs that actually says what the properties of the solution are. It basically forces, and there's a whole class of solutions that actually has those properties. And it basically writes it in a way, and it uses actually what we know about sine and cosine functions to do the proofs. It's a very beautiful theory. And it basically says that solution is also going to oscillate. It's also going to have zeros. It's going to have infinitely many of them. And those solutions you can actually use as an expansion, just as the sine and cosine functions we've been using. So it's a general theory behind that. And so I'm going to do that, I think, in the next 2 lectures, because I think it's necessary. It gives you a very good foundation. And it also explains why a lot of properties we see in nature actually exists. Like those things that oscillate like that is typically if you have a square box, right? You have, and you knock it, then it's going to start oscillating. The frequencies is going to be depend on the shape of the box itself via this coupling with a constant that we've actually done. But the same thing is true if you have a circle, right? You bump it like a drum. It's also going to have frequencies. And those frequencies are actually going to depend on the solution itself. But we know we basically are going to prove you always have those frequencies. And similarly, if you have an ellipse, you knock it, it's also going to have frequencies, different frequencies. And so you can actually then design the ellipse to choose the frequencies you want. So it's a way of tuning an instrument. And that is true in general, right? And that property is a direct result of this theory. It also has implications if you start going for 3 dimensions, right? If you look at our atom, you're basically solving Schrodinger's equation, but in 3 dimensions. Excuse me. So you once again going to have the case where you get Helmholtz's equation. You want to solve Laplace's equation equals to a constant. You can also separate it. So you get 3 different differential equations, ordinary differential equations. All of them actually fall into this class that we're going to look at. All of them are going to oscillate. And the ways in which that oscillation is fitted in actually determines the frequencies, which determines the energy levels of your atom. So the fact that hydrogen has certain light waves that it sends and energy levels is directly as a result of this Schrodinger theory that we're going to do. We're also going to prove that there's a complete expansion, that you can either represent it in the one way or you can represent it on the basis functions. So it's a very fundamental theory that is used several places. So so that's about it. So that's what's going to happen next time. Take a look at this. It's not complicated, but the technical stuff, you must master the complex transformations before, before we go on. And I'll give you, I think I've got an exercise that actually illustrates it. So, thank you. I received both your problem sets. I'll try and give it back to you tomorrow. Any questions at this point? It's kind of nice. It's a change of approach from the Green's functions. I'm very fond of it. It's also, in 2 dimensions, I've now removed the art form. When I learned it was basically try different guesses, transform it into different things, and then maybe you get it separable. People have become famous by doing that. I think the guy that taught me how to do that, I did my PhD with, became famous because he actually found some equations in relativity and he separated them, which meant that people could then go about solving them. So he did that as his PhD work and he became famous as a result. So I don't think he didn't use this. He just basically tried for about a year and a half. And a lot of people had tried before him, and he knew that if you could do it, it's like, there's certain problems that if you take them out, you allow a lot of progress to take place. And he knew it was one of those because people wanted to use it. And then he succeeded, and he immediately got a very fancy job as a result. He's taught a lot of people. So there's certain basic skills, like a gymnast that can suddenly tumble. Some of these things are like that. If you can just find your way through, it's amazing. So typically, if you want to make a good PhD project, you pick one where something like that is possible, but it's still possible to get an answer even if you don't. Because if you then get the big result, that's wonderful. You always want the chance of that, but you don't want to risk your whole PhD project on actually finding something like that. So anyway, that's it. All for me.